Hello friends, in my this video I am going to discuss about tuned amplifier. Okay, this is basically one frequency selective network, and what is its importance? It has its own application in wide range in the communication system. Okay, suppose you have made one receiver. When different frequency signals are received by the receiver, but you want a particular frequency of a particular signal of a particular frequency, then you have to use the tuned amplifier to extract that particular signal of a given frequency from the others. That is how you can, this will act like one basically amplifier which will not amplify all other frequencies, but it will amplify a particular frequency of signal so that you can easily receive that one. Okay, so this is basically tuned amplifier. So basically, if you intuitively try to understand, you will get gain versus frequency curve like this. See, at particular frequency omega naught, the gain is very high, and nearer to that, if you consider any frequency like omega naught minus just some value, see, gain is reduced. Okay, at omega naught only there is a high peak. Okay, so that at the signal which has frequency omega naught, that will be highly amplified, and all other frequencies will be not amplified by that extent, and as a result you can that amplified signal will be dominated over other frequency signals so that you can easily receive your own signal. Okay, so basic idea is the gain versus frequency curve we have to make like this. For we have to design a certain circuit like this, that which will have gain versus frequency curve like this one. Okay, it will amplify a certain frequency, it will amplify very high value in a particular frequency. So how we can design such circuit, that's what I am going to discuss in my this video. Before that, you just observe this parallel resonant circuit which you already studied in your network theory and fundamentals of electrical circuit course in detail. Okay, already in first semester and second semester, I hope already you know this, that for this circuit y of j omega, if you represent in terms of frequency domain, that is equal to 1 by r plus 1 by j omega l plus j omega c, because the impedance offered by the inductor is j omega l, so admittance will be 1 by j omega c. Impedance offered by the capacitor is 1 by j omega c, so admittance is j omega c, and impedance offered by the resistor is r only, so here admittance is 1 by r. And as the three connections are in parallel, so that if you are calculating admittance, you will simply add those three, right? So now you just take common j and you will get y of j omega is equal to 1 by r plus j into omega c minus of 1 by omega l. What property I have applied here? 1 by j omega c equal to minus of j by omega l. As you know, minus of j equal to 1 by j, right? This basic concept I hope you know from the concept of complex number. Now you just try to observe this particular equation and see for which value of omega this y of j omega will be minimum. Obviously y of j omega minimum value is equal to 1 by r, that is we have to make this complex part equal to 0, right? So because this part is only frequency dependent, this is the real part, so that what we'll do, we'll make this part equal to 0, so omega c minus of 1 by omega equal to 0, so omega c equal to 1 by omega. So that frequency, if you term as omega naught or resonant frequency, that is equal to 1 by root over of LC. So obviously, as we get for series resonant circuit, similarly for this circuit also, the resonant frequency is 1 by root over of LC, or you can say f is equal to 1 by 2 pi root over of LC, because f is equal to 2 pi, sorry, omega naught equal to 2 pi f naught, right? These basic things. Now, see, we are getting y of j omega minimum at 1 by root over of LC. And at omega equal to 0, what is the y of j omega? See, if you observe the term y of j omega, if you take magnitude only, you just observe at omega equal to 0, y of j omega will have very high value, because at omega equal to 0, this term will become infinity. Okay, so that if you take magnitude, you will get very high value of y of j omega, right? Similarly, at omega equal to infinity, what you will get? At omega equal to infinity, although 1 by omega will be 0, but omega c will have value equal to infinity. So that in that case also you will have very high value of y of j omega. So the curve intuitively we can get like this, that is admittance versus frequency curve, that is at omega naught or 1 by root over of LC value, the admittance is minimum, and as you go from towards omega equal to 0, admittance increases. As you go towards omega equal to infinity, also admittance increases. If the admittance curve is this one for various values of omega, then obviously no doubt the impedance versus omega or resonant frequency, impedance versus omega curve will be just reverse of this admittance versus omega curve, and that will look like this. Now you see impedance versus omega curve, this curve and this gain versus omega curve is just similar only. So if we make able to make such circuit for which gain is dependent on this Z, this impedance offered by the parallel resonant circuit, then our job will be done. Because if gain is dependent on Z, then that gain also vary like this kind of impedance versus omega curve, and we will get our M, that is making tuned amplifier whose characteristics curve looks like this. And one more thing, what is the Z value? Z equal to 1 by Y, right? And you got Y equal to 1 by R plus 1 by j omega L plus j omega C. So that Z equal to 1 by R plus 1 by j omega L plus j omega C. This we will use later, okay? So now idea is clear that we have to make such circuit for which gain is dependent on impedance like this fashion, okay? So see how we can make this circuit. Very simple. This is the circuit, okay? See what I have done here. Normal MOSFET common source amplifier only. Just here coupling capacitors are added. Source is directly grounded. Here we have applied AC plus DC, and here VDD is there for keeping this in saturation region so that it acts like amplifier. As you know, common source act like amplifier in the saturation region only, and across RL we are taking output. So if you consider that already using DC analysis concept, we have made this circuit in saturation, we have designed such that the circuit will be remaining in the saturation region. So if we able to make AC analysis, and if we able to show that gain is dependent on impedance, and this circuit can be reduced to parallel resonant circuit, then our job will be done. Okay, so what we have done, see, as our intention is now to do AC analysis, so we'll short circuit all the DC source, VDD will be removed and Vin will be directly grounded. This VDD will be grounded and this capacitor will be short circuited and will not consider internal capacitors. Okay, again to make a explanation simple, so that our new modified circuit will look like this, where RL is there, capacitors are short circuited, coupling capacitors here, V input is AC source, and this capacitor and inductor are there connected with the ground here. What we have done, just replaced VDD by ground, okay, and short circuit the capacitors as we generally do in our AC analysis. Now what we do, just replace this NMOS by its small signal equivalent model, and see Vin is applied in the gate. So Vin is equal to basically VGS. Now from drain to source, GM VGS current flows. R0 is the MOSFET output in resistance, and this L and this capacitor, this RL is present. Why? See, if you consider this as MOSFET drain, obviously, see the inductor and capacitor are connected in between MOSFET drain and ground. So that's see here also nothing changed. In between drain and ground, inductor and capacitor are connected, and this RL is basically connected in between drain and ground, and similarly here also in between drain and ground, or you can say drain and source, because source is short circuited with the ground. Okay, so this becomes our circuit. Now we have to analyze this. No need to think about this left hand side because this is not connected with the right hand side. Just we have to apply the concept of network theory and we have to analyze this circuit. Very simple. See what we have done here, same circuit, V input equal to VGS for this particular circuit, and if you apply nodal analysis, assume all the currents are coming out of this particular node, okay, and if you apply KVL in this node, you will get GM VGS, that is this outgoing current, plus V out minus 0 by R, that is current flowing through the resistor, plus V out minus 0 by 1 by j omega C, that is current flowing through the capacitor, plus V out minus 0 by j omega L, that is current flowing through inductor is equal to 0. Okay, and you will get, just take j omega c up in the upper and or in denominator, and you will get this expression. Okay, and then if you arrange this, you will get gm into vgs, or vgs is equal to v in, right? In this particular circuit you can clearly understand from this. So gm v in equal to minus of v out into, just I have taken common v out, and we are getting 1 by r plus 1 by j omega l plus j omega c. So what is V output by V input, or what is the voltage gain for this particular circuit? That is equal to minus of Gm by 1 by R plus 1 by j omega L plus j omega C. Now this term is, you just observe, this is equal to this Z we can write, right? Because Z equal to 1 by R plus 1 by j omega L plus j omega C. So replace Z in this particular equation, and you will get V output by V input, that is gain or voltage gain for this particular circuit, is equal to minus of Gm into Z. Now you know that see, observe this particular circuit. If you observe what I have done here, I forgot to mention one thing here. R0 and RL, these two resistors are there, right? So these two equivalent resistors I have replaced by R. Okay, where R is basically the equivalent resistance of RL and R0 parallel connection. Okay, this is one very important point. And you just observe this particular circuit. This is what? This is nothing but parallel resonant circuit whose impedance versus frequency curve we already studied, looking like this, right? So basically for this particular circuit, impedance versus frequency curve look like this, and we have derived that for this particular circuit the voltage gain is proportional to the impedance. So in this particular circuit the gain will also vary like the impedance variation with respect to the frequency, so that we will get, as the gain is dependent on Z, and Z versus omega curve looks like this, so that we can get gain versus omega curve also looking like this. This minus sign, what it symbolizes? This minus sign indicates just the output is 180-degree phase shift compared to V input. As you know that common source amplifier acts like NOT gate, or it has 180-degree phase shifting property. If you ignore that, because 180-degree phase shift will not affect in our particular this circuit analysis, we already have achieved our aim, that is we have made such circuit which will have gain dependency on the frequency like this one. Okay, and we have made this kind of circuit so that now this receiver can amplify a particular frequency. We can design it at so that we can design according to our need, that is we can adjust the omega naught value by changing inductance and capacitance, and we can amplify our desired frequency signal in a very high amplification factor, and attenuate other frequency signals, so that we can basically get our desired signal. Okay, so this is very important analysis, very simple. This is very small topic but very important. Often in analog electronic circuit or in semiconductor device or circuit paper you may get questions based on this, but the basic idea is very simple. Okay, if you able to remember this circuit, then analysis is very simple. Just replace the MOSFET by its corresponding small signal model and apply nodal analysis. You can do mesh analysis also, your choice, but I found that nodal analysis is easier for this particular circuit. Anyway, now what you should know, for what you should have a clear idea while analyzing this circuit, how to replace the MOSFET by its small signal model, what is MOSFET small signal model, and how to handle problems related to small signal model. If you have doubt, please go through the link given in the description. I have already made a separate playlist for the small signal analysis based MOSFET problems. If you have doubt, you can check that. Okay, this is all for this video. I hope you have understood the working of the tuned amplifier. This is very important. If you have any doubt, you can ask in the comment section. Thank you for watching.